So let's talk about sound as we start Unit 3. It's Section 3.1 anyways. It's Chapter 11. Chapter 10 is waves, which will technically be the beginning of this unit. Sound is a continuation. So don't focus too much on these numbers, 3.1, okay? But Unit 3 is entitled Sound here. So for Chapter 11, we're going to talk about sound. So you've likely heard the riddle. And show me your hand if you've heard this riddle. If a tree falls in the forest and there's no one there to hear it, does it make a sound? Have you heard that little riddle before? Okay. I always thought that was a dumb sound. I mean, or a dumb riddle because, of course, I mean, it just crash. I mean, it does. Of course, it does make a sound. But when you think about it, people have different ways of viewing this, right? Most people say, don't be stupid, move on. But physicists attempt to answer this question. In order to do this, we need to first know what sound is. So what is sound? When you hear something, a wave of energy vibrated the air, which traveled down your ear canal, vibrating your eardrum. And this is interpreted by your auditory cortex in your brain as sound. All right? So, as I've mentioned before when we first started talking about waves, the reason why you can hear my voice right now is because inside my throat area, okay, in this area here, my vocal cords are vibrating. And they're vibrating in such a way that the air molecules, the molecules of gas and mixture in the air, they are being disturbed. They're vibrating slightly. And those particles are bouncing into other particles that are in the air. And there's a series of compressions and rarefactions, and that's getting to your ear, and it's vibrating your ear in the same way that it's vibrating from my head. So when we talk about, here's a wave, what is the frequency of the wave, and what is the frequency of the source? Okay, your eardrum is vibrating the same as my vocal cords are, to a certain, to a certain extent, because that energy disturbance is being transferred through the air into your ear. A physicist looks at the wave of energy. So if we're talking about physics in this class, we're looking at the wave of energy that has vibrated the eardrum, and we would call that sound, right? The wave is the sound. This is something objective and constant that can be measured and studied. So a physicist would look at this riddle and say, of course, it makes a sound because it would cause the air to be disturbed in such a way that it would make a wave that our brain interprets. Now, the philosopher would look at this same riddle and say, at this situation, says, well, without the brain there to interpret the wavelength, it's just energy, and is it really sound? And the philosopher might say that it's the brain that gave the expression to the wave, and therefore the sound only exists in the brain. This means that each sound is subjective, and that's interpreted by someone, and cannot be measured by anyone other than the observer. So if we take a look at science, you may think, well, yeah, it's a wave of energy, it makes a sound, end of story. But you may say, well, listen, what is sound if it's not interpreted by my brain? Like, there are many sounds apparently being made across the world, but I can't hear them. So is that actually a sound? Do I actually know what's happening? If no one is around to hear it, can we call that a sound? I mean, these are good questions. But in physics, we're going to look at the wave of energy, and that's what we're going to look at. So, a physicist, obviously, as I've mentioned, would look at the situation and say that the tree would generate a wave of energy in the air when it falls. They would also say that it can be studied, so that's the part of sound that physicists would be interested in. A philosopher would say there's no one there to observe it, and so the sound doesn't exist. Of course, in this class, physical science, we're interested in studying nature, and we've already started studying waves, and so we're going to study this as a physicist would study it, and talk about sound in terms of waves and the quantity, quantifying those kind of things. All right. Since sound is a wave, its wavelength can be measured. Okay, so waves are produced when sound is made, And each sound has a specific wavelength, and it also has a specific frequency. Okay, so humans can hear sound between the frequencies of 20 and 20,000 hertz. So if a sound is made and it has a frequency of cycles per second between 20 cycles per second and 20,000 cycles per second, humans can interpret that energy. Frequencies below 20 hertz are called infrasonic. Infra. Right? Infrasonic. And frequencies above 20,000 hertz are called ultrasonic. Okay? Ultra. So infra would be below our threshold of hearing. Ultra would be above our threshold of hearing. See that humans have a range of hearing, so we can hear sounds that are between 20 hertz, that's 20 hertz, and 20,000. So here's 10,000, here would be 100,000, so here would be 20,000, okay? And this scale looks to be a little, a little bit weird. This is not how you should make a graph. But to go from 10 to what is this, a million hertz, all these would be like little specks. So they've created this a bit. Anyways, so if we look at us, we can hear sounds here. There are some animals, like a cat, and even a cow. And where's the dog? Dog's up here. Okay, look at their range of hearing, okay, is a little bit higher than our range of hearing. You see that? And so that means that dogs can hear sounds that we can't. You've heard of a dog whistle before, right? Someone blows a dog whistle, this is what we hear. But the dog hears a very high whistle, and they're like, what's going on? What very high frequency noise? Okay? And so their range of hearing is a little bit higher. So that's why if you have a dog whistle and you blow it, okay, if it's working properly, generating a frequency that's really high, then there's lots of animals that can hear it. I guess even cats could hear it, right? Probably, because they can hear sounds with very high frequencies. The beluga whale, okay, again, very high frequencies, and the bat. The bat operates in super high frequencies, so they can't hear anything below about 2,000 hertz, but they can go up to 100,000 hertz. Looks like so bats, when they generate sounds and communicate with each other, often we can't hear them. It's like little clicking noises and stuff. But there's and they, of course, they use their sonar to locate things, right? Their sonar location. So we hear the their mouths and different parts of their body making the noises, but we can't hear the noise they're making, but they can. Okay, so that's the range of hearing. Any questions on that? Okay, so I don't have a chart for transmitted sounds, but in your textbook there on page 351, there is a range for transmitted sounds, and what we see is some interesting things there. A typical stereo system would generate sounds from 15 hertz up to 30,000 hertz. So the lower frequencies would be the bass notes, right? They travel quite a bit better. They travel through things a bit better. That's why if someone's coming down the street, you can hear the thump of the bass in their car or whatever before you can hear the high pitch, the other sounds. But some stereo systems will generate frequencies below what we can even hear, right? And of course above what we can hear as well. What else? A human, okay, that's a stereo system. A human can generate sounds from about 85 hertz to about 1100 hertz, this chart says. Okay? So from 20 to 20,000, we can't even generate a high enough pitch, a very high pitch that we couldn't hear ourselves. But that's the transmitted sound. Okay, so the bat can generate super high frequency sounds. 10,000 hertz is the lowest sound a bat can make, which is right at the top end of our range. The green frog, this one's pretty interesting. The green frog can generate sounds from from 50 hertz to 8,000 hertz. It's quite the range. And you see other interesting things there that generate sounds that are really high. A robin, a porpoise. Okay, and look at the silent dog whistle. It starts at 20,000 and goes up from there. The dog whistle is 20,000 to 24,000 hertz. All right, so 11.2 in your textbook, page 352. If sound is a wave, then it needs a medium to travel through. Okay, so one of the important things about Okay, so I'm going to show you a video here. It's animated and just talks about the transmission of sound. So just listen to this.
Vibration is the back and forth movement of an object. As you speak, vibrations are produced by the vocal cords in the throat. You can hear only when the sound energy reaches your ears. But how does sound energy travel? Wonder how that works? Come, let's go across to Dr. Zook. Sound energy travels in the form of sound waves. There are mainly two types of waves, transverse wave and longitudinal wave. Let us see how waves travel. We can use a slinky spring to observe both types of waves. Emily is holding one side of the slinky, while Dr. Zook is holding the other end. With a quick upward flick of the wrist, Dr. Zook has sent energy traveling through the slinky. Notice how the slinky moves. This is a transverse wave. In a transverse wave, the particles vibrate at a right angle to the direction of the wave. The wave traveled from Dr. Zook to Emily and back. Now let's see what a longitudinal wave looks like. Emily is holding one end of the slinky, while Dr. Zook is pulling its other end towards himself, and then pushing it towards Emily. Watch closely, and you will notice that some of the coils crowd close together, and then slowly move farther apart. This is because the vibrations are parallel to the direction of the wave. If the wave moves from right to left, then the particles also vibrate from right to left. This is a longitudinal wave. Sound waves are longitudinal waves. These waves travel at different speeds in different mediums. The medium could be a solid, liquid, or gas. Now let's see how this works. In a solid, the particles are very close together. Sound energy moves as one particle hits the other particle. With the particles being so close together, sound travels quickest through a solid. If we look at particles in a liquid, they appear to be slightly further apart when compared to solid. Thus, sound energy takes a little longer to travel through a liquid. Look at the particles of gas. They are spread out, and hence, sound waves travel most slowly through them. Now we know how sound travels in different media. The vibration of particles produces waves. Wavelength is the distance between two consecutive compressions or rarefactions. The number of waves passing through a point in a second is called frequency, and it is measured in hertz. Sound waves travel in all directions. Sound gets reflected. That is, it bounces back on hitting a solid surface. Bouncing back of sound is called echo. Bouncing back of sound is purposefully used in detecting depth of sea depths. That's amazing, isn't it? Summary. Every sound is produced by a vibration. Vibrations are produced by our vocal cords when we speak. There are two types of waves, transverse wave and longitudinal wave. In a transverse wave, the particles vibrate at a right angle to the direction of the wave. In a longitudinal wave, vibrations are parallel to the direction of the wave. Sound waves are longitudinal waves. Sound travels quickest through a solid. Wavelength is the distance between two consecutive compressions or rarefactions. The number of waves passing through a point in a second is called frequency, and it is measured in hertz. Bouncing back of sound is called echo.
All right. So there's a little summary video. Did that help? Yes. All right. Well, you can watch it again. It's on YouTube, on the World Wide Web, and you might be able to access that from home. No, we're not going to watch it again right now. But you guys can watch it if you need to at home. Okay, very good. All right, let's continue on with our notes here. Most of the time when we're hearing sound travel through the air to our ears, when we hear sound, it's coming through the air. As we learned in the video, and as we've mentioned before, sound can travel through any medium. I don't know if you guys have ever tried to listen to sounds underwater, yelled messages to each other underwater. Sound can still travel. You can still hear things happening under the water, although it's muffled and it's a little bit hard. It's harder to see underwater. It's harder to hear underwater because of the medium, right? If you're trying to see through air, that's fairly easy compared to seeing through, a lake or pool of water, right? Same thing with hearing. All right. Perhaps you've used a string in a can. I don't know, as a child, maybe I don't know if you guys have ever tried that. But if you take an empty, clean out a tin can, a can of beans or something, and you clean it out, wash it out, and you stick a hole in it, put a hole in the bottom with a nail or something, and you stick a string in there, and you tie a big knot, and you tie the other end of the string, a really long string, to another can on the other end. You can kind of play the telephone game, right? And you can talk into the can on one end, and if the string is fairly tight, the other person can actually hear you fairly well. So I don't know if you tried to do that, but that sound is actually coming through the solid. It's coming transferred through the can and the string and into the other can and to your ear. All right. You may have seen old westerns too, where someone puts their ear to the train to tell if a train is coming. Anyone's ever seen that? Okay, some of those old movies. Okay. You ever wonder why they do that? Well, it's because sound travels faster in metal. And so if a train is far away, it's obviously causing the tracks to vibrate, and that vibration will travel quite a bit faster than the sound will travel in air. And so if you consider a train making a sound on a track, way over here, it'll travel faster in the track than this up here is how the wave travels in air. So, if you put your ear to the train track, apparently you hear something, there's a train coming well before you can hear it through the air. I wouldn't suggest that you find the nearest train track and put your head on it. That would not be a good idea. Hey, I'm doing a physics experiment. No, you're going to be doing a death experiment if you do that too much. But anyways, you get in trouble there. Metal is denser than air, so waves travel through it faster, as we just saw in the video. And actually, it's about 17 times faster. The fact that sound of the train arrives first in the metal and then in the air tells us that sound does have a measurable velocity. And that's where we're going to get to next here in our study, is the actual speed of sound in air. Likely as a child, you would count the seconds after lightning flash while waiting for the thunder in order to tell how far away the lightning is. This works if you know the speed of sound in air and at that temperature, okay, and at what temperature it's at. Luckily for us, this is consistent and can be calculated using this important formula. So you want to write this formula down right here in your notes. It's the speed of sound in air. It's measured in meters per second, and how it's calculated is this. 332 meters per second is the temperature of air at 0 degrees Celsius. Now, as the temperature rises above 0 degrees, the sound actually gets faster. And how that's calculated is you multiply the temperature in Celsius times 0.6, and then you add it to 332. Okay? Now this is for the speed of sound in air. And so if we take a look at the formula here, okay, so the speed of sound in air, let's say here we go, speed of sound in air is 332 plus 0.6 t. Okay, that's how you might write that just in kind of math terms. And let's say the temperature is, what's the temperature today? It's a pretty nice day. Actually, tomorrow it's supposed to be 27 degrees. Can't believe that. Yes, yes, in October. Anyway, so let's say it's 27 degrees, and so what would the speed of sound be in air at that temperature? Well, we could just do this right here. 332 plus 0.6 times the temperature in degrees Celsius, which would be 27 degrees, right? Now, you don't have to worry about your units there because it's going to be in meters per second. But what is 0.6 times 27? Anybody got that? What's 27 times 0.6? 16.2. Okay, sounds about right. And so the speed of sound in air here is what? 348.2 meters per second. Okay, so at that temperature, the speed of sound would be about 348 meters per second. Okay? Now, 348 meters in 1 second. Okay, if you think about, I don't know how many of you guys have done track, all right? One time around the track is about what, 400 meters, right? One time around a big, the track, right, that you guys run on. So that's about 400 meters. So almost one full time around the track in 1 second. That's how fast sound can travel in air. So almost one full time around the track. And you think sound travels really, really fast, and it does, but it doesn't travel as fast as light, right? Light travels extremely fast. Sound travels at, about 350, on a warm day, 350 meters in 1 second. Does anyone remember how fast light travels in meters per second? It's a little bit faster than 348. It's 300 million meters in 1 second. So light travels really, really fast. Sound travels really, really slow compared to that. I don't know if you guys have ever been at a baseball game. If you had a baseball game, and if you're sitting, quite a ways away from the plate where the batter is, and you were watching, even if you're playing outfield. I played outfield when I was your age. I was in grade 12, playing outfield, and playing, what was I playing? Left field, I guess, for most of the season. Anyways, all-star, but I'm not going to brag. But anyways, I remember watching the bat, every pitch, I would watch the bat, and you always would see the bat make contact with the ball before you'd hear it, right? And even if someone's on the other side of the school ground or whatever, and they're yelling to you, or they clap, right? That sound, it comes to your ears just a little bit after you can see them clapping. So that's light traveling quite a bit faster than sound. I don't know, again, we go back to track. If you guys, run a race and you got the starter pistol, right? Well, if that person is standing 100 meters down the track, it's a 100-meter race. If you're watching, I mean, it's too close to really make much of a difference. But do you notice that there's smoke that comes out of that starter pistol gun? Now, I don't know. This was back in the day. Maybe that doesn't happen anymore. They don't have the smoke. But anyways, I don't. Do they still have the smoke? Anybody know? Okay, back when I was in high school. Anyways, it was like a big cap gun, and they would shoot it, but you'd see the smoke pop out there before you'd hear the sound. So, I mean, I don't know if they'd call a false start if you left on the smoke and not the sound. It'd be too close to call, really, but there is a difference. There's a difference between when you see it and when you hear it. And that's the whole point, that sound has a measurable speed. It's quite a bit slower than the speed of light. The speed of light is really fast. So this formula, it should be noted, is just for air. Okay, it's not for different materials. For helium, okay, the speed of sound in helium is 1,440 meters per second at zero. So not 332, but 1,440 meters per second. And this actually, you might find this interesting, this is actually what leads to your voice sounding higher pitched when you breathe helium. So if you take a big breath of helium from a helium balloon and then you talk, do you notice how your voice gets really high and really, high frequency sound? Okay? That's because the air that you're breathing is passing over your vocal cords quite a bit faster. And the sound that your vocal cords are making, I should say, the sound from the vocal cords are traveling faster through the helium. And so it's coming out of your mouth faster. And it's not being kind of slowed down. Because, you hear someone, if you slow it down, it always goes lower, right? But if you speed something up, it always goes higher. Okay? So it's the rate at which those waves are hitting you, right? Hitting your ear. Faster wave coming in more frequently, higher pitched sound, which we're going to, again, talk about later. All right. So, yeah, that's that. Do you have any questions?